Аким, привет, меня слышно?
Привет, тебя слышно.
Да, мне просто вчера парочка студентов прямо под вечер написали и сказали, что у них нет доступа к курсере, ну, к курсу. Можно тебя попросить, пожалуйста, собрать ФИО и как бы подключить их? Я не знаю, ты это делаешь ли через учебку, но, в общем, у нас есть студенты на потоке без доступа к курсере.
Да, окей. Спасибо, что сказал. Я
Мгм.
тогда займусь этим. Ну, прямо скажем, курсер не основополагающий, но в любом случае он полезен.
Ну, я понимаю, да. Нет, я просто был подключен давно, на самом-то деле. Там же я так понимаю, тоже студент в КН в прошлом. И там,
Нет.
может, если... нет? Ну, в общем, у нас там раз в семестр была рассылка, что как бы есть онлайн-курсы на курсере, можно подключиться, и то есть раньше подключали.
Я понял. Не, у нас такого счастья не было, к сожалению. Так, давайте еще минутку-две подождем остальных. Сразу такое замечание, что я так вижу, мы, конечно, все на русском понимаем, но сегодняшнее занятие, в принципе, как и все, у нас будет записываться, вот, и выкладываться для тех, кто хочет его, не знаю, смотреть потом, поэтому на английском проведем, вот. Очное занятие. Ну, короче, да, если что-то прям совсем вам непонятно, можно спрашивать на русском. На самом деле, по ходу того, как будем это изучать, поймете, что на английском deep learning даже легче это проходит, ну, просто потому что иначе приходится кучу таких терминов, которые на русском ну, совсем не звучат, переводить. Часто бывает так, что потом что-нибудь, ну, вот эти всякие концепции типа перенос знаний говорят на русском, и ты вообще не понимаешь, о чем речь идет. Okay, so I hope some other students will join us promptly. For now, let's discuss some preliminary moments. First of all, hi, dear students. My name is Tsvigun Akim, and I'll teach this introduction course to deep learning. First of all, I'd like to discuss two main goals of our course. So I know that you have, during the previous year of studying, you passed a lot of theory in machine learning, and I was told that you are just desperate to code all of this. And here I would like to disappoint you that our course won't consist just of coding, because the main goal of our course is to prepare you for the next specialization courses like NLP and so on. I'm not sure whether you'll have some courses like CV or speech recognition. I know that you for sure will have the second part of this course devoted to natural language processing. And our aim, our goal is just to be ready to this, to know all the main concepts of deep learning, and to know how all of these operate in practice, so that when you start coding some NLP tasks on your course, you won't have any problems with understanding how this or that works, why all of this works and gives us a good result. And the second point is that I can be honest, I was told that I will teach this course not long ago. So I prepared this course myself. So, and as I myself work in this sphere, I will try to include in our course only those concepts which are important when you work as a deep learning specialist. So just quick examples. For instance, today we'll speak about the extensions of the gradient descent. And the ones who watched the first video of the first week of the course probably remember that it consists of different optimization methods like momentum, Nesterov momentum, ada delta, ada grad, and so on. But in practice, all that we use is ADAM or in more rare cases, SGD. The ones which are not used, we will not discuss them on seminars just because they are useless in practice, and having an understanding of how, for instance, ada delta works will not give you any benefits. So all that we discuss here on our classes will be only those concepts, those things that are very important on practice or a bit more rare that can be asked on different interviews when you'll try to apply to big companies. Okay, so probably some other students will join us later. The plan of, two more things. The first about the question for our course. About the grade for the course, how is it constructed? So we gave this online course previous years to students, and their reviews were awful. They said that the tasks on Coursera do not develop any skills. They're just like you need to fill in 2 or 3 lines of code and then wait for 3 hours to ensure that your code hasn't crashed. So we decided to stay away from Coursera tasks. So in case you want to do them, you feel that doing Coursera tasks will develop some of your skills, you're free to pass them, but they will not influence your grade for this course. The grade for this course will consist of 2 parts. First of all, it's the tests that I guess we will have 3 tests. We'll have 3 offline classes, and then each of them will start with writing a test. These will, I don't know how to say, occupy probably 40% of your grade, and the other 60% of the grade will depend on your grades for your homeworks. You'll have 2 homeworks. The first will be devoted to general directions of deep learning and computer vision, while the second will be devoted to NLP, and probably, I'm not sure for now, probably will embrace some of the methods dealing with outliers or probably autoencoders. I guess that's all. Yeah. As usually, I also have not spoken about this. While we're having online classes, we have a chat here. So we have a chat. We do not have it. Yeah, there it is. Great. So if you have any questions, write them in chat. I always see what you write there, what is okay, I see everything right there. So, and I will try to answer the question as soon as possible, because I myself was a student not long ago, and I know how it works, that you listen, you have a question, you don't understand everything that goes after this thing which is not easy for you, and then you say, okay, I don't like this, I understand nothing, and then you never appear on the classes anymore. So feel free to ask everything that is not understandable for you. Moreover, usually it works this way, that when you have a question, it means that half of the group, or probably more, students have the same question as well. And when you ask it, they feel like, okay, great, somebody asked it, because I think I was dumb, that I could not get this. In case I do not see the chat and you ask a lot of things and I don't answer them, feel free to enable your microphones and ask this using your voice, because sometimes I also can forget about this. For now, probably that's all about all the preliminaries for our course. Yeah, one more thing. I also know that it's very difficult when you have an online course and you are told, like, you will watch the video the week of the course and then we will discuss it. I know that more than 50% of students will not watch it, and that's okay. We'll have it different way. So first of all, we will discuss some things, some concepts. Then you will watch the videos and how to say it in English. Okay, you'll make your understanding of these topics better. Then we'll probably, before our tests, which will consist of several questions, describe how, or probably calculate the convolution of something, and so on. I will always send you the list of possible questions that can appear on our tests. Probably for numerical tasks, only the numbers will differ from the ones that I sent. So if we had a class and you watched the video of the course and you still do not understand anything, you must write in the chat, or if you are shy, you can just write privately to me and ask this, so that it doesn't happen this way, that you did not understand this, but then you find it on tests and you say, like, oh, I could not understand, that's not my fault. So we study something here. You watch videos of the course. When I send you the list of questions, you just prepare for them and are ready to answer them on tests. Then write the tests. And if all these 3-4 steps take place, I will not promise that you will never forget this material that we learned, but probably it will stay in your memory for much longer than if you just read this one time and then never use. For today's class, I asked you to watch the first week of the course, and the first week of the course is, as far as I understand, is just revising the material that you learned previous year. Linear models, overfitting, gradient descent extensions, and so on. So the plan for today's class will, first of all, as I could say, according to the poll, not all of you have a good understanding of how neural networks work. So first of all, we will recollect some gradient descent techniques and how it works in practice using a small linear model. Then we will extend this model to a neural network to understand how neural networks are composed, how they work, and how they are trained. Then we'll quickly speak about the extensions of the gradient descent that are applied in practice. And I hope this will be the biggest part, but for now I'm not sure. We will see how a small neural network can be built using Torch. If we have enough time, I will write these from scratch. And an important task for you will be to take your computers and write it together with me as well. So when we will write the code together from scratch, of course, you will understand much better what happens there. If we do not have much time, then we'll quickly explore the notebook which I prepared for today's class. Yeah, and probably it will be like a small homework for you to write a copy of these on your own. Okay, so if there are no other questions, I guess we can start. Okay, so let's speak first of all a small revision of the material. We have linear models. We have linear regression, which is applied with regression tasks. And we have a logistic regression, which can be used when we have a classification task. Never mind, this is a binary or a multi-class or multi-logits classification task. So how logistic regression is trained? Can anyone please tell me? No one remembers? No one.
Sorry, the question was how linear regression trains?
No. How a logistic regression is trained. Okay, I'll give a small prompt. There are two ways of training a logistic regression. The first way, which was used long ago before powerful computers appeared, is a kind of a theoretical way of fitting it. And the second one is the method which is used in practice and scikit-learn and so on.
You mean logit and two sets, two data sets, training and test sets, or you're asking something more complicated?
No. I am asking about the method of getting the weights for logistic regression. You have your training set, X train, Y train, and you need to somehow train your logistic regression, which means getting its weights. Either this is a feature or a vector weights in case of a binary classification task, or a matrix if this is a multi-class task. Okay, so before we continue, let's come to agreement in this, that your participation in seminars is not included in the final grade, but if you are active on seminars, I remember this, I will increase somehow the grades for the tests, for instance. So in case you are active, I'm on your side when checking the tests. In case you are not active, I'm neutral to you. Yeah. Okay. So
do you mean the logit thing with the exponential, with exponents in a fraction? No.
yes, that's, you speak about the sigmoid function.
Yes.
I think we find the weights,
The
I mean,
logit.
like the parameters through the likelihood function. No, there was something like this. Like
Great.
maximizing the likelihood.
Yeah, that's a good answer. So the theoretical way of getting the weights for, or the weights for logistic regression is using the maximum likelihood method. But this method is very complicated and requires a lot of computations, so that it used to be, it was used previously about 20, 30 or probably more years ago, for finding the weights, because using this method we can calculate it manually, but doing this on computers requires significantly much computations and much memory than using classical stochastic gradient descent. So all the logistic regressions you can find now in Python or probably R if you use this language. By the way, yeah, for our course we'll code only in Python, no R. For this course you can slightly forget about this. Yeah, what was I speaking about? Yeah, it's trained using gradient descent. When you use these from scikit-learn, you can just press Shift-Tab and make sure that the method for learning the weights is stochastic gradient descent. I'm sorry, I'll have to leave you for 1 minute. Please wait. Excuse me. Yeah. Okay. So there are some different extensions of gradient descents, like LBFGS, for instance, and probably this is used as a default method for in scikit-learn. But anyway, all of this refers to gradient descent methods, which are used for learning the weights for now. So the first thing that we'll do is we will derive the updates for the weights for logistic regression, and we'll see how a backpropagation works and can be extended for some bigger models. So for now, I will enable my. So you can see my interactive desk now, right?
Yes.
Perfect. So let's use the most simple example when we have the task of the binary classification. So our model, can somebody tell me how many logits will we have to output using a model? One or two for a binary classification task?
I'm sorry, what 1 or 2? I mean, let me hear.
How many numbers, okay, our model will need to output?
Oh, one number,
Because-
zero,
One number, yeah.
0 or 1, if it is two-class classification.
Yeah, it's two class a binary classification, and if
I
we
mean, not one number, probably the probability. Yeah, so like the one number probability.
yeah, and if our model output two numbers, will this always lead to mistakes? Okay, it can output two numbers in case we use softmax as an activation function. Yes, and cross entropy as the final loss. Is it me who has a bad network, or does everyone hear me well?
Oh, I hear you well. Yeah.
Okay, great. So our model consists of two groups of parameters. That's the feature vector V and the intercept coefficient V nil. So let's derive the gradients for this and for this. So we have our training sample X, and we take some kind of a batch from it, which we'll refer to as current batch. Yeah, this can be probably slightly difficult. Let's come forward for a second. When using gradient descent, but probably most of you remember this. When using gradient descent, if we use all our training data, we usually run out of memory because as a rule, you have about several thousand or several dozens of thousands data examples. And when you try to calculate some mathematical operations on this entire array, it requires a lot of memory. So when using gradient descent, we use usually we use either the stochastic gradient descent when we have only one example per batch, or sometimes, not sometimes, but in 99% of cases, we use mini batch gradient descent when you take just a small number of examples for each batch. Some conventional numbers for the batch size are 16, 31, 64, 128, just some numbers divisible by 2, just a conventional way for this. No motivation behind it. Okay, so the X is the current batch of features. Y is the current batch of target variable. As we have a binary classification task, each yi will be either nil or 1. So first of all, let's see how our model generates predictions for each element of the batch. What do we need to do? First of all, the linear transformation, x multiplied by v plus v nil. And then we apply the sigmoid function, which transforms our number, which is obtained here, to the diapason of from 0 to 1, so that it can be interpreted as the probability of that the instance belongs to the positive class. Let's refer to this as y hat, just y predicted. And for those who forgot how the sigmoid function operates, here is the decoding. That's y divided 1 divided by 1 plus exponent of minus z. So in case z is equal to nil, this will be 1, and the full expression will equal 0.5. So 50% that it belongs to the negative class or to positive class. So this is the example which lies on the boundary between the two classes. If it goes to plus infinity, this comes to nil, exponent of minus infinity, and we've got 1 here. So when z is close to infinity or is very large, this expression is very close to 1. In case z goes to minus infinity, this part will be plus infinity, and the full expression will go to 0. So it means like when z is very small, the probability that the instance belongs to the negative class is very high. Is this clear for now for everyone? Because all the things we'll do from now will be slightly harder. So in case you have any questions, please ask them now. Okay. This is called the forward pass of our model. So how our model generates predictions for a feature vector. And now we'll need to derive the backward pass of our models, which means how backward pass is used to calculate the gradients for our parameters. So our loss. For binary classification task, the loss is, please somebody remind me.
1 over n multiplied by sum of not correspondence, like where is not what we predicted.
Not precisely. Okay, I'll write this. Thank you anyway. This loss is called the log loss function, and its formula is as well. So we have a minus here. And we've got logarithm of our predictions in case our predictions, the true class is equal to 1. So this is a positive class. This will be better. Plus logarithm of 1 minus predictions, which is the same as the probability of the 0 class, multiplied by the that the true labels equal to 0. And yes, one more thing which I forgot to discuss. For now, I will refer to all of these as a vectors. So this is a vector, this is a vector. It means like this is an indicator function for each component of y. On your previous classes last year, when deriving these formulas, have you used the same notions, or should I probably write this first of all element-wise? In other words, is this formulation clear for everyone, or probably for someone that's difficult? Yeah, if you are just too shy to say this, you can write to me privately so that nobody will see. It's clear.
Is it? We usually take regression of the probability, or not the regression, take the logarithm of the probability. So the formula.
Yes, and this is a probability as well. I see. That's not clear. You say that y hat is usually referred to as the predicted class. Okay, if you used kind of notions, let's name it with P. This is the probability that we predicted. Okay, great. So this is our loss function. And to get the gradients of our parameters, I need to get them the gradient, just the gradient of the loss by these parameters. Let's derive how this will look like. So what we need to find is this and this. So to see, we need to see how much the loss function depends on each of these group of parameters, and the gradient is the direction where our function, in which our function grows mostly. In just the direction where our function will grow as much as possible if we slightly increase our parameters by a very, very small number e. And so the anti-gradient, which is simply minus our gradient, is the direction where the function decreases as much as possible. So since this is our loss function, we need to decrease this as much as possible. Our task will be to find the gradient and subtract it from our parameters so that we will move in the direction of the anti-gradient, where our to make our loss function as small as possible, just to minimize. So how can we derive these two things? Here is where the chain rule appears. Can anyone remind me, please, what the chain rule is?
The chain rule is how we take the derivative. I mean,
Of functions of functions.
yeah, functions of functions. Yeah, if we take the derivative of function, it's derivative of the outer function multiplied by the derivative of inner function.
Great, thank you. Is there anyone who forget about this, and probably we need to quickly get over this. I hope not. Okay, so chain rule, it will appear in week 2 of the course. It means if we have now this, we can write is this way. We can take the derivative of the function by another group of the parameters. For now, this will be p hat multiplied by the derivative of p hat with respect to our parameters. So we can write this as follows. For now, let's leave it as it is and find this part. So this is, yeah, okay. So starting from this moment, let's find the gradient when we have just one element in the batch. So we have a features vector x small y, and we have only one number as an output. When we derive all the components and we see how they look like, we will simply extend them to the case when we have a mini batch which consists of n examples. Okay, so yeah, let's do it this way. Py, which means that we have only one number here. The loss looks like 1 divided by n, which is 1 in our case, multiplied by logarithm Pi in case y original equals to 1 plus logarithm minus p hat in case yi equals to 0. Okay, so it looks like we have to write this as a condition, but later we will see there is no need for it. So in case yi equals to 1, this part will be equal to 0, since this part equals 0, and we have only this, which will be derivative logarithm y divided by y, and this is an elementary derivative which looks like this. But in case our predictions are just the true class is negative, we'll need to take this part and we'll have 1 minus py divided by, not divided, of course, just the derivative with respect to this, which will look like 1 divided by 1 minus the hat multiplied by the derivative of the inner function, and the derivative of this inner function is just -1, since we have this minus here. So we will have a minus, yeah, I forgot this, I'm sorry. Since we had our minus here, right? Before the function we'll have minus here, and here we'll have 2 minuses. This one, which comes from the derivative of the inner function, and this one. So totally we'll have a plus here. There it is. So this is in the case yi equals to 1, this in the case yi equals to 0, but we do not want to have a kind of condition here, and we want to have just an expression which can be applied in both cases. To do this, we'll need to do the following trick. Let's multiply this part by yi and this part by 1 minus yi. So if we multiply this part by yi, this, I have not written this explicitly, when yi equals to 1, when yi equals to 0, right? So if we say that this is how our derivative looks like when yi equals to 1. So yi equals to 1, and we can multiply our expression by 1. The same works here. We say this is when yi equals to 0. So we can multiply this expression by 1 minus yi, since this equals to 1, right? That's clear for anyone, right? Okay.
Yes, it is clear. Yeah.
Great. So, and now we can just sum these two parts and see what it looks like. By yi plus 1 minus yi divided by 1 minus p1. And let's see what happens depending on which class yi belongs to. So if this belongs to positive class, this part is taken, just this is 1, only this is taken. And here we've got 0 in the nominator, right? So this part will be 0. In case yi belongs to class 0, this part will be 0 as well. And this part will equal just to 1 divided by 1 minus py, since the denominator equals 1, right? So we have the full formula for the gradient with respect to the probability we predict, since we can see that in both cases it equals to the right expression. Now let's make this expression even better. We will just simplify it slightly. We need to multiply just to have the same denominator here and here. Let's do that. We have minus yi multiplied by 1 minus ei plus 1 minus yi multiplied by py divided by probability of the positive class multiplied by the probability of the negative class. And totally, we have minus yi plus py yi plus py minus py yi divided by pi multiplied by 1 minus py. And these two, okay, let's continue here. This can be simplified, and we get just this py multiplied by 1 minus py. There it is, the full gradient of a loss with respect to the predicted probability. Okay, so this part is calculated. Now we need to calculate this part as well. These calculations are clear for everybody. Yeah. If not, please ask. We'll be happy to answer. Okay, so the second part equals this, and we can use the chain rule here as well. So instead of calculating the gradient of this sigmoid function of the inner expression, we can decompose it into two parts. It will look like this. I will explain what zy means. Let's say, yeah, in this case, we have only one example. Let's say that this is the zy. So the linear transformation, the result of the linear transformation is just zy. In this case, we have the following. Let's calculate the first part, is gradient. We'll have 1 divided by 1 minus ze is derivative by ze, right? This is 1 plus exponent of ze in the power of -1, since we divide by it, and its gradient with respect to zy. So first of all, let's take the derivative of the outer function, and it will look like -1 multiplied by 1 divided by 1 minus exponent of minus zy squared, right? So we'll have -2 power here, which means which is the same as dividing by the square of this function. And we need to multiply by the derivative of the inner function, and the derivative of the inner function, can somebody tell me what it is?
It's just x.
I'm sorry. Could you please repeat? Don't be afraid to say, because I'm just start worrying that no one keeps up with us.
It's xi.
It's like minus e to the power of minus.
Great, yeah, that it is. There it is. Thank you. By the way, how do you call this? Xy. Let's see. How did you just call this minus xy? How? Because I just could not. Probably I referred to.
I was saying that the derivative of I mean the second multiple was xi. The derivative of zi.
Xi.
With respect
exponent.
to w.
I
Yes.
get. Oh, yeah.
My
Thank you.
mistake.
Thank you. Great. Yes, there it is. So this minus and this minus can be removed, and totally we get this, which can be decomposed as this multiplied by this. How can we name this part? Using our, I'm sorry? Could you please repeat?
The sigmoid.
Yeah, and using our.
It's actually p. It's our prediction p hat.
Great, and this. Yeah, that's probably not obvious, but if we multiply this part,
it's p hat over e to the power of.
Yeah. Thank you. You are right, but we will decompose it and see how beautiful it can be simplified even more. So we have this. Part. Let's multiply both the numerator and the denominator by e in the power of zy. Okay. So in numerator we have simply 1, since the powers will be killed, and in the denominator we have 1, which is obtained from multiplying this by this plus exponent of zy. Does this remind you of something? Okay, this is actually the sigmoid of minus z1, right? Because if we had the sigmoid of z1, we would have a minus here, but since it is just killed here, we can have the minus here. So this part will look like exponent of minus z1, which is actually the exponent of zy. And the sigmoid of minus z1 is the probability of belonging to the class 0.
So 1 minus p hat.
Great, there it is. Is this transformation clear for everyone? Or probably we need to Okay, I hope this is clear, but to ensure it is, I will write this in slightly different manner. So we had it this way, and let's do the following. Let's subtract this part from 1. Just we'll have 1 minus Z1 minus Z1. We'll have 1 plus E minus Z1 minus E minus Z1 divided by 1 minus E minus Z1. This is killed. And E, this is just the sigmoid, right? So this, we know that if we subtract 1 from this part from 1, we'll have the sigmoid of Zy, which is the probability of belonging to the positive class. And since summing up this and this gives us 1, we understand that this is just 1 minus P hat. I hope that probably this will be slightly easier for those who find it difficult to get the first way. Okay, so let's leave it as it is. And as a result, we have 1 minus P1 multiplied by Pi multiplied by Pi. What we need to find is this part for now, right? And this part is found very easily. This is just the derivative of xy multiplied by v plus, oh, of course not I, this is our parameters, plus v nil, which is just constant with respect to v, since they do not depend on each other. And we take the derivative of v, which is just xy, right? So let's take all together and find the update rule, the gradient of our parameters when we have this one example xy. We have the derivative of loss with respect to the predicted probability multiplied by the gradient of the probability with respect to zy multiplied by the derivative of zy with respect to our parameters, which is here, I'll remind you, we had Py minus Yi divided by Ey multiplied by 1 minus Py. Here we had simply Py multiplied by 1 minus Py, and here is just xy. So as you can see, we can do this, and the gradient simply looks like this. This is the gradient of our loss with respect to our parameters v. Let's quickly find the same thing for v nil, since it will not differ significantly. We'll have this same in the beginning, just the gradient with respect to the predicted probability, the derivative of probability with respect to zy, and here we'll have this, just this in common. From here we can see that it gives us Py minus Yi, and this, can anyone tell me what this will be? Let's write it here. 1, that's perfect. That's exactly 1, since we have just, we will have the, with respect to v nil here, which is just taking this part, finding its derivative, it's 1. So this is just, looks like this. So we have the gradient of our feature vector, our weights vector v, and our intercept v nil. Okay, let's extend this to the case when we have several observations in a batch. So this is for one example, and let's now write the dimensionalities of everything we have here. So this is just a scalar number 1 by 1, and the feature vector has some kind of dimensionality, just 1 multiplied by m, since this is a vector. And what have we? Yeah, feature vector is of the dimensionality 1 multiplied by m, vinyl 1 by 1. This is a scalar and intercept. So when we have several observations here, instead of having x small y, we have a feature matrix now, which we'll refer to as x, n observations, and m features, right? What do we also have? P will now be again a vector, since we predict for all the observations of the mini batch with the dimensionality n by 1. And y is also a vector, n by 1. So when we have several observations, of course, I'm sorry, I always mess up the notions from NumPy and linear algebra. Of course, when I have a vector, it's like, it will be easier to say this way. By the way, this doesn't matter, of course, whether you have n by 1 or 1 by n, but probably just when I write this, this is like a vector which we are used to see in NumPy, like this kind of reveled vector. Of course, a conventional way of linear algebra is having a vector like this, and then of course we'll have n rows and 1 column, which is n by 1. But I hope this will not just cause errors in your understanding. So p minus 1 will have a dimensionality 1 multiplied by n. X is a matrix of shape n by m, and the total shape equals to 1 by m, which is exactly what we need to update our feature vector, our weights vector, I'm sorry, v. In the case of v new, yes, of course, as now we have a mini batch, let's go back for a second. We had it probably, yeah, we had this part 1 divided by n, and when we had one observation, this was 1, but since now we have a mini batch of size n, we need to recollect this part, and totally we'll have it this way: gradient of loss of mini batch with respect to v. But here comes the problem, a small problem. The update rule for our intercept vector was like only this, but now it's the vector of shape 1 multiplied by n, while vinyl is just a scalar. What do we need to do in this case? The answer is simple. When we wrote it here, we said you can see the cursor which I'm moving on the screen, right?
Yes.
Yeah, we can.
Great. So here we said it equals just to 1. But of course, when we have a vector here instead of one scalar zy, when we have a vector z, it will consist of n components. And here we have only one parameter. So we would obtain the identical vector here, just the vector of size n with all the elements equal to 1, because we'll have to get the gradient of each of the component of the vector with respect to our parameter, which will be 1, 1, 1, 1, and so on n times. So this logic would be applied here. The identical vector, I forget, I guess this is how it can be denoted, right? Please correct me if I'm wrong. Something like this, if I'm not mistaken. Never mind, we'll take it n by 1, or we'll have it transposed and when it's 1 by n. Anyway, as a result, we'll have multiplying this by this means just simply taking the sum of the components of this vector. And then we do not forget to divide by 1 by n, and totally we'll get 1 by 1 here, right? So this is the gradient of loss of our mini batch with respect to vinyl. So this is the gradient for V. This is the gradient for vinyl. Okay. Are there any questions on this? Probably something was too difficult. Okay. I hope you really do not have any questions. Let's speak in a more general way. Here we used the chain rule twice. First, to calculate the gradient of loss with respect to the predicted probability, and second, when we had to calculate the gradient of the predicted probability with respect to our parameters. But if we want to make our model more difficult and we need to add some more functions and some more parameters, what can we do? The first thing, which is probably seems obvious to someone, probably, is making like this. We made now the forward pass of our model and the forward pass of a logistic regression looks like this. But what if we add some parameters so that before making this transformation, we'll make another one so that it will look like X feature matrix is multiplied by some weights matrix V nil. It's just the notion, doesn't mean that it has in power of 0 something else, plus some intercept vector V nil plus, oh, I'm sorry, multiplied by feature vector, feature matrix V1 plus intercept. If we do it like this, and of course taking the sigmoid of all the result, can somebody tell me whether we will have a better model or not? Just can this model outperform the previous one? Well, of course the answer is no, but probably someone knows why the answer is no. Okay, that's all right. So in fact, we have two linear transformations here. Here is the first linear transformation. Here is the second linear transformation. And the combination of linear transformations is a linear transformation. So in fact, this model will have a lot of more parameters than this, since here we had m+1 parameters, and then we'll have the, if the size of this matrix is some kind of k m by k, so that we'll have this k by 1, here we'll have k by 1, 1 by 1, and totally we have mk plus 2k plus 1, which is significantly bigger than this, right? But in fact, since this is just a combination of the previous model, and it cannot outperform this. But
mk squared, no?
I'm sorry.
Isn't it mk squared? Because we multiply m by k again.
No, m by k by 1, k by 1, 1 by 1.
Yes.
But that's not critical anyway. That's not important for now. We just see that it has a lot of more parameters with having the same just power. But if we add some nonlinearity, which is not used in linear models, linear, okay, let's have it as it is. So we will be able to first transform our data to some nonlinear space and then return it back to, not return back, but what can we do is add some nonlinearities. So instead of having just linear transformations as it is done in linear models, we'll have some more difficult, more complex transformations, which generally can grab some more difficult dependencies in the data, since you probably know that in real data, the case when the dependence is linear or clear to linear is not always the case. So as a rule, we have some much more difficult dependencies, and adding nonlinearities will help us understand, will help our model get and model these very difficult dependencies. So after we did a linear transformation here, we can add some nonlinearity. According to the poll, all of you know what activation functions are, but let's quickly revise it one more time. Activation functions are functions which consist of small, not small, but computationally efficient transformation, just one small nonlinear transformation, which can transform our data, which can add some nonlinearity to our transformation. Probably not very clear how I describe this. Let's just see some examples of activation functions. The first and the most popular is ReLU. It does the following thing. When we have a vector, when it gets the vector z, it does the following transformation. Okay, for simplicity, for now, let's write all these functions for just one element. This will be much simpler to understand. And this is zy in case zy bigger than 0, greater than 0, and nil otherwise. This is this very function. Sigmoid, this is also one of the activation functions. We know already this, it's this. And another one function, which is very used rarely, but sometimes it is still used, is the hyperbolic tangent, which looks like, if my memory serves me right, 2 multiplied by, not 2, like this. Why? Probably I am wrong here. Please correct me, but I hope not.
Correct.
Yeah. Okay, so how do they look? The ReLU function looks like this. So when our thank you, when our value z1 is less than 0, we'll have just the 0, and here we can write it like this using the school geometry. This is a very simple yet effective nonlinear function, since absolutely any difficult function can be approximated with the combination of ReLU functions. So when we use 5 or 10 ReLU transformations, we can approximate any function. The sigmoid, you probably remember this. It looks, yes, here is the 0, here is 1, here is 0.5, and it looks like this. What's interesting, it goes up to 1 already when x equals to 4. The sigmoid of 4 is 0.99. Yes, ReLU has discontinuity since this is just an indicator function, but as we will see now, that's not the problem for us. And hyperbolic tangent, very few space left. It looks like this. So here is 1, here is -1. But both of these transformations require significantly more computations than ReLU function. We can see that here we need to take the exponent of minus our value, and here we need to take the exponent of our value and the exponent of minus our value, and then divide all of this, which requires a lot of computations, a lot of more than ReLU. Moreover, ReLU can, as already said, approximate any nonlinear function, and that's why ReLU is used in neural networks much more often, just because it's simpler and yet it's very effective. It adds, I would not say a lot, but just it adds nonlinearity to our data. So we can add this activation function here. Let's have it ReLU here. And what we'll have, we have a linear transformation. Then we get the result of ReLU function of it. So we add the nonlinearity, and then we make another linear transformation. And since we added the nonlinearity here, this expression cannot be this is already a nonlinear transformation and cannot be simplified like this. Then we take the sigmoid again, and we have one number. But as we did added the nonlinearity here, in case there are some nonlinear dependencies in our data, it can be approximated much better than when we use just one linear transformation. I hope that's clear, right? Okay, so, and this is how neural networks work. So they consist of two parts. First of all, they have a linear transformation. Then they add some nonlinearity to our data. Since if we add linear transformations sequentially, we can simplify it using only one linear transformation. So linear transformation, add nonlinearity, non-linear transformation, add nonlinearity, and so on. This is the principle of working of neural networks. Of course, there are some more difficult layers like attention layers. Oleg told me that the previous year you had a small talk about it. There are some layers like dropout, which are simple, but I can't say they either do linear transformations on nonlinearity, but let's leave it for later classes. For now, just these are the two main components of the neural networks. But how can we get the update rules for weights? How can we train our models so that we have a good weights here, 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 here? The same way as we did for logistic regression. So we applied the chain rule, and after we found the gradient for these two parameters, like in logistic regression, then we need to find the gradients of the loss with respect to this and this group of parameters. What we need to do, we need to again apply the chain rule so that our update will look like this, is equal to the loss by this, not 0, let's have it just like this. This is what we have already found, and now the expression for this. And now we'll have this, how V1 depends on V nil. And here we'll need to, first of all, find the gradient with respect to ReLU. As it was correctly mentioned, it has discontinuity, but when we have the automatic differentiation, which is, for instance, used in PyTorch, it will be just, it will not cause any errors, but the problem is that when for those parameters which are greater than 0, the derivative is just themselves, and for those who are less than 0 or equal to 0, their gradient will equal to just 0, because the result is 0, and if we increase the result by a small value epsilon, it will not change, right? Since it is 0 anyway. This is one of the problems of the ReLU function, which is caused the problem of the diminishing gradient, but for now that's okay. The main thing which you should remember is that, okay, we have, instead of having the full gradient, we'll have a kind of condition, but that's not the problem. So what, for instance, PyTorch will do, it will see, okay, we have a condition. So for each parameter, I will update, have the update rule following the condition. Of course, it's very difficult to write this manually on paper, but for computer programs, that's of no difficulty. So there it is, how neural networks make a forward pass predictions, how they work, and how we can update the rules for them just using this very technique called backpropagation. If there are any questions, please ask them. By the way, yes, I thought that this part will take significantly less time, but we also have to discuss some of the extensions of the gradient descent. Let's do the following thing. As far as I remember, you do not have classes right after this. Let's just take some time from our break. We need about 10-15 more minutes. We'll speak about the extensions of gradient descent. And as for our first neural network, we'll leave it for the next class, because now I think that it's better that we write it manually together, and we will, how is it said, we will unite our classes together with some special layers of the neural networks, which will be used in our network. Okay, let's do it like this. So in case there are no questions here, let's move on to the extensions of gradient descent. For now, what have we done? We derived the gradients of our parameters. But why would we always update our parameters with respect to only the gradients on the current iteration? That's the first question. And the second one is, which learning rate do we need to have? Okay, we have some kind of our general learning rate for our gradient descent method. Probably we have some kind of learning rate schedulers, which also update learning rate according to some according to some rule. But for usually it happens that some parameters tend to fluctuate significantly and some do not, which means that we need to have different learning rate for different group of parameters. And here are two main directions of extensions of gradient descent methods. First of all, change the update rule. The second, change learning rate parameter wise. So for each parameter will have a kind of its own learning rate. Let's quickly speak about the most important methods from here and from here. Here, the simplest method which implements this logic is the momentum methods. What does it say? It says that when we have a mini batch gradient descent, sometimes we need to, sometimes our batch can be non-typical or consist of a lot of outliers and so on. And in this case, the update rule will be very noisy. And if we were moving very well on the previous iterations, this iteration can just hit us away like this, somewhere far away, and we will probably never return to our minimum, to our optimum point, or probably we just have a lot of more iterations required to have our algorithm come up to the optimum point. So it says the following: let's accumulate the information obtained from the previous iterations. So in case of just updating according to the gradient on the current iteration, we'll somehow use the results on the previous iterations as well. And the weight for each previous iteration, for the gradient on each previous iteration will decay exponentially. What does it mean? I have a variable vt on iteration t, which has the following VQ plus our learning rate multiplied by the gradient of the loss with respect to our parameters, loss params. So to update this variable, we take its result on the previous iteration with a weight gamma, and we add our just the update rule, which would happen using a classical stochastic gradient, just gradient descent, when we have a learning rate multiplied by the gradient of a loss by parameters on the current iteration. Yeah, it's like this. And to update our parameters, we simply have our parameters on the previous iteration minus VT. So instead of taking only this part, we accumulate the previous information about the gradients. This value of gamma is usually taken around 0.9. So usually about 90% of the update rule is occupied by the gradients on the previous iterations, and only 10% by the result on the current, so that the direction where we are moving is very stable. So it does not, in case we have some kind of an outlier batch now, it will not hit us away from the right direction. In this group, there is also Nestor of momentum. As I said in the beginning, we'll not speak about it, so since it's not important for us and is used very rarely, let's speak about this group of extending gradient descent methods. By the way, everyone has understood the momentum, right? No questions about this. I hope so. So here are also a lot of methods like ada delta, ada grad, and so on. A lot of them not used in practice. Let's speak about the RMS prop. It's also very rarely used separately in practice, but we'll in 5 minutes we'll discuss why do we need it. So this method modifies the learning rate for each group of parameters the same way. It says now we add this kind of let's estimate the square of the gradient of our parameter on current iterations. But instead of just taking the square of the gradient on current iteration, let's mimic the same logic as it was in momentum, and we'll have some kind of accumulation of the results on previous iterations. What is it used for? This is used to understand whether our parameter was changing significantly on previous iterations or not. In case it was, and it was fluctuating very much, we need to diminish the learning rate for it, so that will make it the future changes will make them smaller, so that will prevent from having these parameters go some far away. So we have this part which has the following formula. So that's the square of its gradient. Since it's just one parameter, okay, this is a scalar, this is a number, this is a number, this is a number. So the formula is taking with 90% its previous value, and with 10% the square of the value on the current iteration. And so the update rule for this parameter will be as following. We have a general learning rate of our model, and this general learning rate will be divided by this expression, squared t plus small epsilon, in case this is very close to 0, to prevent the learning rate from be divided by 0. And here is the gradient or some update rule what we have. So the logic of RMS prop is to accumulate how the gradient or how the parameter accumulate the information about the previous gradients of our parameter, and if it was high on previous iterations, we need to diminish the learning rate for it for now, so that will prevent it from being very volatile and will make its changes more stable. Any questions on this? Okay, so here is the momentum, here is the RMS prop, and why have we discussed both of them? Because we need the method ADAM, which is used in 90 or probably more % of neural networks for now in NLP, in CV, in speech recognition. And ADAM consists of 2 parts, of momentum and of RMS prop. It has 2 parts. First is MT, which is updated like according to the logic of momentum, plus 1 minus B1 on its current gradient. GT is the gradient on iteration T. I've used this notion a lot, but have not spoken about this. And VT is the member for calculating the learning rate parameter-wise. Yeah. So both of these variables accumulate their information on previous iterations, and with some small share, they add the gradient and the square of gradient respectively. So the update rule is okay. So this is how they look like. And I can say in advance that these values are very high. The authors of this method propose beta 1 equal to 0.9 and this 0.999, the proposed value. And let's speak about the first 100 or 1000 iterations. So on first iterations, we initialize the values with 0. And let's speak about VT, for instance. After 100 iterations, we have this plus this. Okay, after 100 iterations, as this was initialized by 0, after 100 iterations, this 0, the initialization value, will be multiplied by B2 on the first iteration, by B2 on the second iteration, by B2 on the third iteration, and so on. So 100 iterations, it will be multiplied by this value. So after 100 iterations, the initial value, the initial 0, will have the weight of this. Probably I am wrong, but I think that's about this. Oh, I'm sorry, about this, or probably less. Okay, probably it's even 0.5. That doesn't matter. It means that after 100 updates, which is already a big number of updates, we still have this 0, which was just used for initialization. It does not reflect the logic of our parameter, the logic of its change. It still has a very large weight. And if we update the weights our network using this rule, we'll have very biased results because they will very much depend on the values, how to initialize v-nil and m-nil, right? So to prevent this influence of the initialization values for these parameters, the authors propose to calculate their unbiased estimates, which are calculated as follows: mt divided by 1 minus beta 1. Vt hat is calculated like this. So yes, and these are unbiased estimates. So after 100 iterations, we'll have this value divided by number less than 1, which will so if we initialize them with zeros, this unbiased part will only contain the information which was accumulated during these 100 steps rescaled by this part. So the update rule for Adam looks as follows. I'm sorry, I have some problems with connecting my board. Yeah. One second. Am I right? Maybe I forgot the T component here. Yeah, of course. I'm sorry. I forgot this because on the first iteration, we need to take only this part rescaled by 1 minus beta 2. But after 100 iterations, the accumulated information is a lot more that it was on the first iteration. So we need to rescale. Here is the power. So b1 in the power of t, like 0.9 in the power of 100. So that's obvious when we have 0.9 after 100 iterations, this first initialization part will not influence the result. But for instance, in this case, it will. And the final update rule in our Adam optimizer looks like this: square of Vt plus epsilon to prevent division by 0 multiplied by mt. So here is how Adam works. So it combines the ideas of RMS prop and momentum methods. Are there any questions here? Please ask them if you have any, because probably I can say it this way. Probably when you do deep learning, you do not always think about how this or that optimization method works, but these questions can be very often asked during different interviews, like in Google, in Facebook, or if you want to stay in Russia, in Sberbank, in Yandex. Yeah, so it's very good to understand how it works, because when you have some difficult models which consist of very complex unusual neural networks, and you have a good view of how this or that optimization method works, it will be easier for you to get good results. The last thing, I'm sorry for taking the time of your break, just for 1 or 2 more minutes. I'll show the notebook. Moreover, I will even send it to a chat, but we will discuss it later. We will discuss it on our next class. There it is. So we have our data, we download it, we preprocess it, we scale this. We'll speak about the scaling next time, but that's a very important part of neural networks, that the input must be scaled. Then we train our, we process our data, we prepare some data sets, we build our model, and then we have our train loop. And as a result, we compare the result of our neural network with some linear regression, with ridge regression, and we can see that it significantly outperforms both linear regression, ridge regression, lasso, and so on. There it is. So if you have a wish and time to look through this notebook, that's great. It will be easier for you to understand it next time. If not, okay, we'll still discuss it. Mikhail Andreev asks, why would we need to rescale M and V? Yeah, so let's see what we had on in the beginning. So let's take the first iteration of this. We initialize them with zeros, and V1 equals to nil multiplied by nil 1 GT squared, right? And so we take the gradient, which was just the purpose of this accumulation is to use the results on previous iterations, but now we have no previous iterations. And if we take this part and may put it here, it means like we increase our learning rate by, instead of taking only the results on the previous iteration, like GT squared accumulated with some weights, we have nil 1 multiplied by GT squared. So we can say that this part will look like 10 multiplied by square of 10 multiplied by GT, right? So, of course, I'm sorry, not multiplying by 10, but of course dividing by 10. And since we divide and divide it here, we multiply our learning rate by 10 multiplied by square of 10, right? And that's not good, because in this case, we do not accumulate the previous information, but we simply diminish the information that we get on this step. V2 will look like nil 999 multiplied by the previous value, like this, plus G2 squared multiplied by nil 1. And again, this is a very small number, since we have it here and we have it here, and that's not good, because the main part of this variable is occupied by this initialization value nil. So to make this estimate unbiased, we need to divide it by the weight which has this initialization value, and on each future iteration, it will have the weight b here, b2 in the power of t. That is. Yes, it's important only for this. It's important for about 30 or 50 iterations. After this, the initialization, the weight for initialization member is very small. And here we need it for several thousand of first iterations, since, as you can see, multiplying by this on each iteration will decrease the value for the initialization very, very slowly, right? So even after 2000 iterations, it will have a rather big value, and we will still need to calculate the unbiased estimate of this. Great. Yeah, hope it was clear. Okay, so group 181, thank you. Thanks everybody, right? It's it. I hope to see you next time on Saturday next week. We'll have an offline class, but next time, well, to be honest, I'll think how to do it better, because next time I do not want to write a test, because we still have not passed much theory. But we'll have a coding class, and probably your presence is not important. Okay, so we'll see how to do it better way. I'll write in our conference in Telegram. Okay, thanks. And now, yeah, we have our class with group 181. Hi, everyone. Yeah, let's just have a 1-minute delay. We'll wait for some other people who will, I hope, will join us promptly, and so we'll start. Yes, the recording of the seminar will be released. Yes, and in case I will forget, please remind me to send you the notes for our class. Okay, so that's 11:12. I think we can start now. Group 182. Hi, everybody, once again. My name is Tsvigun Akim, and I will teach the classes on Intro to Deep Learning. First of all, let's speak about the preliminaries for our course. The first question, probably the most intriguing for some of you, how the grade for the course will be calculated. As you can see, we have you have your lectures on Coursera, and we have some practical classes here, but the tasks on Coursera in this course, they're useless. So most of them are like write several lines of code and then wait for several hours to check whether your program does not break. So we listened to the reviews of the students on previous years and found out that it's better to refuse from these Coursera tasks. So the grade for the course will be calculated as follows. 40% will be taken by the test. We'll have 3 tests. Yeah, during our classes. I hope that we'll write each test on each offline class. It will be like several questions. Yeah, an important notion about these tests is that each time I will warn you about that. We are having a test in advance, and I will list the. I will send you the list of possible questions so that you can prepare to. If you prepare to all of them, it means that it's easy for you to get an excellent mark. Anything, just the only thing that I can do is that if that's the numerical task, for instance, calculate the convolution of some metrics, I will, of course, change the numbers in the preparing tasks and the real tasks, but I think that that won't be the problem in case you learn everything well enough. The next point, the goal of our course. I'm sorry, I forgot to finish about the grading system. So 40% occupied by tests, retests, and other 60% is taken by the homework grades. I'll have 2 homeworks. The first one will be devoted to general deep learning concepts and computer vision, and the second will be devoted to NLP. Probably we will include something like outliers detection there, or speech recognition, or autoencoders. I'm not sure for now, but it depends on how quickly we will embrace all the topics of deep learning. The next point, we'll have 3, I hope 3, not 4 online classes. For now, in your timetable, you have 3 online, 2 offline, and 1 more we need to think of. I hope it will be offline as well, to write a test there without any difficulties. But anyway, we have a chat here. And in case something is difficult for you, you do not understand something, it is very important that you write to me, that you stop me and ask me to go over it once again. According to my practice, when you have a question, it means that a lot of students in the group also have the same question, but they are probably too shy to ask it, or usually they think like, okay, probably it's the only me who is so dumb, who doesn't understand this, and I would better not ask this because what other people would think about me. And when that very guy asks this question, you feel like, okay, great, I did not understand this as well. So when you have any questions, please feel free to stop me, to ask me to explain this once again. In case I forget about the chat, or I don't see it, or something else, and your question remains unanswered for several minutes, again, feel free to enable your microphone and ask this with voice, because this can also happen. The next, the goal of a course. Here, I would probably slightly disappoint you that the main goal of our course is to prepare you for the next specialization courses like NLP. So what does it mean? It doesn't mean that we will not have any coding, any practicing classes at all. But for now, I think that about 50% of the time during our classes we'll speak about theory, and other 50% of time we'll code, we'll do some things. By the way, I hoped that today's class will be devoted to coding mostly, but in fact, I doubt whether we will at all get up to this, because we need to revise a lot of theory, important for you to understand how the neural networks work, how they propagate, how they are trained, how they're applied, and so on. So getting back to the motivation for our course, the goal of it, first of all, it's to prepare you to the future courses. The second, it's of course show basically all the spheres of deep learning. As you probably know, or probably do not know, deep learning consists of just can be applied in different spheres, like computer vision when we deal with images, or natural language processing dealing with texts, or with speech recognition dealing with sounds, and so on, time series, etc., etc. And it's difficult. It's probably impossible to understand, to be able to do the tasks in each sphere on a very high level. Well, of course, there are such guys. Usually they are on top of Kaggle. But if you decide to do science in machine learning, or you work as a deep learning engineer, usually you have some kind of, I would say, specialization here. Of course, you can know all the spheres on a high level, but you'll have some kind of your not favorite, but main sphere probably. Yes, and the goal of this is of a course now is to make you acquainted with all of these spheres so that you can find the most interesting for you, because for some, dealing with images is just brings a lot of joy to them. For others, dealing with text and learning machines to make some logical reasoning, to make it understand the language is very exciting, and so on. And the third, that's probably not about the goal, that's about the program of our classes. I read this program myself, and I work in this sphere. So I will try to, I will not try, I will include only those questions, only those parts of theory or code which are applied in practice, or a bit more rarely, I will speak about some things which are probably not obligatory for you to remember when you do deep learning, but they can be very often asked on different interviews in big companies. So all the things which we will discuss, just they are used in practice. I will not include some theoretical moments which I myself have not used at all. I work in SBER AI laboratory. That's the laboratory of artificial intelligence, together in AI lab and AI institute. Probably you know there is a new structure in SBER. It's just like a separate company, I guess. Yeah, where the Schmidt-Huber is the director of it. I don't know whether you know who Schmidt-Huber is. This is the guy who developed a lot of different complex deep learning methods like LSTM or GANs, which we'll speak about on future classes. Yeah. Is there anything I wanted to speak about? No? I guess no. I guess it's over for the preliminaries of our course. If you have any questions, feel free to ask. If not, let's move on. The plan for today's class is as follows. First of all, we need to understand what are neural networks, how they work, and how they backpropagate. According to the yesterday poll, I saw that most of you know how deep learning work, know how what they consist of, but not all of you remember how backpropagation works. Not all of you remember how neural networks process information. It's important to make sure that everybody understands this perfectly. And if you are asked this question, for instance, on interview, you can easily answer this and excite the interview. I can see, by the way, there are a lot of Vasily Kirienkos. And yeah, that's great. Okay, so first of all, we will see how the backpropagation works using a simple logistic regression. Then we will extend these to neural networks and embrace their structure. Then we will speak about the extensions of the gradient descent, but as I have already mentioned, we will not, in this course, we will not speak about things which are useless for you in practice at all. That is why we will speak only those extensions which are applied on practice and which are probably important to know about. Some useless extensions like ADA delta or the grad will not speak about them. If you are just keen on learning this, I will send you very good materials which can also describe you these methods. But here will not include this. Another one organization moment. I do not expect you to watch the lectures in advance and then speak about this during classes, because watching lectures when a real person tells you something offline is difficult, and listening to the lectures online when this is a recorded course is very difficult. So we will do the following. First of all, we will discuss some theory or some practice moments on our classes. Then you will have to watch the videos of Coursera to make sure you remember this and you understand all of this. Then I will send you the list of questions to prepare for test. You prepare these questions, then you write this test. And after this test, you will have this material, first of all, understood very well. And second, you will have it in your memory for much longer than in case when you just listen or watch this material once and then forget about this and never use it. There it is. Okay, so if no questions, if there are no questions.
Можно задать вопрос? Я не
Yes,
знаю,
sure.
181 группы задавала или нет, но у меня вот на Курсере, даже если регистрироваться с Вышкинской почты, там платный курс, то 7 дней бесплатный, то есть это с учебным офисом уже решается или как?
Yes, I will write this in our chat. All of you who do not have a free access to the course will need to write your surnames and names to me, and I will send the list of all of you to the, by the way, how учебный office is pronounced in English. Study office?
Yes, study
office. Thank you. Okay, so yeah, let's process this after our class. Yeah, pursue any course for yes, any but not this, because this is inherent to HSE, and this is a part of the specialization, which is a special course. Yeah. Okay, so let's start our theory X course for neural networks. First of all, let's recollect linear models. There are linear regression for regression tasks, and there is a logistic regression for linear classification tasks. There are two conventional methods for training logistic regression, which means getting the optimal weights for it. Can any of you tell me about this? Yeah, another one moment forgot to speak about this. As you can see, your participation on seminars is not included in the final grade, except for the tests we will write. But of course, if you participate, if you are active or during our classes, I will forget you. And when checking the results, I will be on your side, will be positive to you. While if you do not take part, of course, I do not remember you, and I am simply neutral to you. There it is. So, 2 ways of training logistic regression. The first one is a theoretical and an old way. The second one is the one which is applied in practice and significantly more novel. No one remembers. Okay, so the theoretical way is using the maximum likelihood method. Have you heard anything about this during the previous courses?
Yes, we did.
Great, but as I can see, probably not all of you remember it, or probably no one remembers. That's not a problem. To be honest, in deep learning, maximum likelihood will be never used. So for now, we're interested in the way which is used to train logistic regression in scikit-learn or in traditional R libraries, gradient descent. All the logistic regressions now are trained using this method because it's significantly more faster and computationally efficient than the maximum likelihood method. Yes, I will, as we continue, I will probably recollect some things which I forgot to say in the beginning. In our course, we will use only Python language. We will not use R because for deep learning, R is used significantly much more rare than Python. Okay, so the way for training logistic regression is using gradient descent. For simplicity, let's assume we have a binary classification task and we need to get the optimal weights of our model. By the way, when we have a binary classification, how much numbers, how much logits does our model need to return? No one understands? Or
Could you repeat the question, please?
yes, how many numbers our model will output? How many logits it needs to output? So we have a feature vector of size m, which is fed into our model. How many numbers will we have in the output?
What's the feature vector? It's the observation vector, or just for one observation we have m features?
For one observation, we have n features.
Okay,
features.
The output is one number.
Great. Why only one if we have 2 classes?
Well, if we take, for example, the log regression, this is the number will be the number from 0 to 1. It's a score. It's not a probability of one of this observation being assigned to class 0 or 1, depends on how we interpret the model. And then we take the threshold and decide which class we will in which class we will assign this observation.
Yes, thank you. That's a great answer. And can our model have 2 numbers outputted? Will this be an error?
Which log regression?
Yeah, for binary classification.
Well, without modification, I think it will only give out one number.
Okay, great, that's all right. But by the way, if our model outputs 2 numbers, that's okay. Instead of using sigmoid as an activation function in the end, we would need to use the softmax function for two classes. So this binary classification will be treated as the multi-class classification task, and that will be okay. For now, binary classification, the model which, by the way, what's your name? I think you're not Vasi.
We always see this. Okay, my name is Mike.
Mike, great. So as Mike has told us, we'll have one logit outputted by a model, and our model will look as follows. We have a weights vector v, which is of size 1 by m, since we have m features, and we'll have the intercept v nil of size, this is a scalar 1 by 1. Let's see how the forward pass of a model looks like. So what is a forward pass is how our model transforms the input data and outputs it. We have a generally we have several observations fed into our model, and we want to get the prediction for each of these observations. So our feature matrix is x of shape n by m, n is the number of observations, m is the number of features for each observation. We make the linear transformation first, is multiplying by feature by weights vector and adding the intercept. Then we take the sigmoid function to make the output of the linear transformation transformed into the space from nil to 1, so that the result can be treated as the probability of belonging to the positive class, to class 1. Here is the forward pass of a model, and we get the probability vector of size, oh, I'm sorry, let's write it here, m by 1, m by 1, 1 by 1, and the result is of shape n by 1, the predicted probability vector of predicted probabilities. Okay, everything clear for now? Yeah, no questions? Special days, great. So, okay, we have the predictions, and now we need to understand what is the loss. So what is that very function which we will try to minimize using the parameters of the model? Does anyone remember the loss function for binary classification task? I can give a prompt. It is called log loss. Probably some of you remember the formula.
Now log p multiplied by y.
Like this?
It depends on the class of y.
Yes. Okay, you were on the right direction. In fact, it's like this. We will take the logarithm of probability to the positive class if the true label equals 1, plus logarithm of belonging to the negative class, which is 1 minus p hat, multiplied by the indicator that y is equal to 0. And all of this...
Avoid using indicators, just write y in the first case and 1 minus y in the second case.
Like, okay, that y here. Okay, yeah, that will be easier.
Scientific notation, just, you know.
Anyway, we will get rid of indicators later when we get the gradient of this. And an important thing is not to forget, first of all, the rescaling by the number of observations, and the conventional mistake, do not forget minus here, since the logarithm of both p hat and y minus p hat are in the diapason from 0 to 1, and the logarithm of both of them will be less than 0. And to make our loss positive, we want to have the minus here. So it looks like this. By the way, if I do not use any lower indices for our variables, it means that they are vectors. For instance, in this case, both p and y are vectors, and just taking the indicator of this means taking the indicator for each component of this vector. The previous group told me that you have similar notations in the previous courses, but if that's difficult for you, please let me know. Okay, so this is taking the logarithm of each component of the vector, and this means comparing each element of the target vector with 1 or 0. That's okay, great. Okay, so that's our loss. And to get to see how much our loss depends on our parameters, we need to take first of all, calculate the gradient of the loss with respect to these parameters. And then we need to move into the direction of anti-gradient of these parameters. Why anti-gradient? Can anyone tell me?
Because we want to, well, in the maximum likelihood, we actually minimizing the minus likelihood, something like this.
Yes, and for gradient descent?
Well, the idea is that the gradient shows the highest point and we need to find the lowest one. So we have to go in the another direction.
Yes, thank you. That's the correct idea, not very correct realization. So the gradient shows us the direction where our function would grow the most, depending on our parameters. But since we want to minimize, not maximize our function, we need to get the direction where our function will decrease the most. So that we, instead of taking the gradient, we get the anti-gradient, which is just minus the gradient with respect to our parameters. So we need to calculate this and this. How will we calculate this? We have a expression here, and if we try to calculate the derivative straight away, that will be a bit hard. So instead of calculating it straightly, we can use the technique called chain rule. Can anyone remind me what the chain rule is? No one remembers the chain rule.
Maybe Vasil can say something.
Maybe Vasil will.
Well, Vasil won't. So we take the first derivative and then we, well, let's just take the derivative.
Okay,
I mean, like,
that's
it's hard to explain. You just know how to take the derivative and then you
decompose the derivative based on some other group of parameters. So instead of calculating this straight away, we can first calculate the gradient of loss with respect to p hat, and then we can calculate we need to multiply this by the gradient of p hat with respect to our parameters. What does it mean? If you want to see how much this expression depends on this, we can first calculate how this depends on some intermediate value p, and then we need to multiply it by how p changes with respect to the original parameters. So chain rule refers to just decomposing the derivative into calculation of several derivatives, which are much easier to calculate straight away. So we can use it like here, this, and let's calculate this. So first of all, we need to find this very part, the gradient of loss with respect to p hat. Let's calculate this. as I used the indicator functions, let's derive the gradient based on the condition. So yeah, as we move to the gradients calculation, let's do the following thing. For simplicity, we will derive it only for one component, so that we assume that we have only one input vector, which refers to one observation, and we need to calculate the loss, the gradient of loss with respect to parameters only for this one observation, because this will be for now much easier for us, and then we will extend the results to the case when we have several observations, like n observations. So we calculate the gradient of loss with respect to one element, py and p hat y. Let's recall how our loss looks like. That is -1 divided by n. N is 1 in our case, so this is just 1 multiplied by logarithm y multiplied by the indicator yi equal to 1 plus logarithm 1 minus py multiplied by the indicator yi equals to 0. And we need to calculate the gradient of this function with respect to p hat y. So let's make this way. If for now we will just decompose these very indicators into this expression. If yi equals to 1, then we have simply the derivative of logarithm of py hat, which is an elementary derivative and has the following form. And here we have the logarithm of 1 minus py hat by py hat, which is, this is already a complex function, right? It's called. So we need first to take the derivative of the outer function and then take it the derivative of the inner function. The derivative of the outer function looks like this, and the derivative of the inner function looks like, can anyone please tell me?
-1.
Great, just -1. Ah, of course, I always forget this. I forget the minus here, and I forget it.
Plus, yeah.
Thank you. So totally, we have this. And let's do the following trick. Since we assume yi is equal to 1 here, we can just multiply it by yi, right? Because this is 1 and it will not change the result. The same logic will be applied here. We'll multiply this by 1 minus yi, since this is 0 here, and multiplying by 1 will not change the result. And let's sum up the expressions which we get here and here. What's the result? We have 1 minus py hat by yi plus 1 minus yi divided by 1 minus py. And let's explore both cases. If yi equal to 1, we have only this part, since here the denominator equals 0, right? This will be 0, so this part will not be included. We get only -1 divided by py hat, as we wanted to get here. If yi equals 0, this part will also be 0, and this part, this will be the denominator 1, and this will be just 1 divided by 1 minus py hat. So summing up the expressions will lead us to correct results without having the necessity to use the conditional expression, right? So let's do it like this. And let's simplify this expression even more. We need to get both parts to the same denominator, which will look like -yi multiplied by y minus py hat plus 1 minus yi multiplied by py hat divided by py1 minus py. And opening the brackets, we have minus yi plus yi py hat plus py minus py hat multiplied by yi and divided by py hat multiplied by 1 minus py hat. Hope you can see this. These two parts are the same. We can get rid of them and totally we'll have like py hat minus yi divided by py hat multiplied by 1 minus py hat. There it is. This is the full derivative of loss with respect to the predicted probability of belonging to the positive class. Are these calculations clear for everyone? Any questions on this? Yeah, by the way, if you anyway are too shy to ask some questions, you can always write them to me privately so that no one will see it. And I will say like there is an anonymous question. Okay, so let's move on. We have the we had to calculate this. We have this. And now we need to calculate the second part, but again, it will be slightly difficult for us to calculate it. And let's apply the chain rule here as well. Let's apply the chain rule here as well and decompose this very gradient. I'm sorry, I'll just leave you for 1 second.
Вась,
Стесняется.
Вась, достань язык из...
Yeah, I'm sorry. Okay, so I'm not back. Now I'm back. So we can decompose this part on 2 parts as well using the chain rule. And this part will look like what is py hat? That's the sigmoid of the inner function of the linear transformation, which is xy multiplied by v plus v nu. Let's refer to the result of the linear transformation as zy, so that py equals the sigmoid of zy. And instead of calculating this straight away, we'll again decompose it using the chain rule. So we'll have the following view. Let's take the derivative of py hat with respect to zy, and then take the derivative of zy with respect to our parameters. Let's calculate this first part. What we have is to calculate the gradient of sigmoid of zy with respect to zy. That is the formula of sigmoid. Everyone remembers. We have write it, yes, but okay, I don't remember whether we wrote this or not. I will repeat this anyway. That's 1 divided by 1 plus exponent of minus zy. That's the sigmoid. So when zy goes to infinity, this member goes to 0 and our result is close to 1. When zy is close to minus infinity, this part will be close to infinity and the result is equal to is close to 0. And when zy equals to 0, we'll have 1 here. 1 divided by 2 is 0.5, which means that when zy is equals to 0, the prediction lies on the boundary between the two classes, between the negative and the positive class. So let's take the derivative of the sigmoid function based on its input. Looks like this, right? As we divide it here, it's the same as putting into the power of -1. And again, first of all, we'll calculate the derivative of the outer function, then of the inner function. Derivative of the outer function looks like -1 divided by 1 minus z squared, because we take this very power in the denominator and divide by the result in the power -1. Yeah, hope that's clear. And now we need to take the derivative of the inner function. Can anyone help me, please, with it? Is this difficult for everyone, or probably vice versa? That's too easy.
No, it's,
Mike is here for me. Yeah.
like exponent to the power of x. The derivative is exponent to the power of x.
Great. Thank you, Mike. There it is. So since we have minus argument here, we'll have the, first of all, the derivative of the outer function, which will be exponent of minus zy, and then we take the inner derivative of this function, which is -1. So that's the result, and let's simplify it. So now it does not look very easily, but as we'll progress, we'll see how easy it can be decomposed. The minuses, we can get rid of them. So we have like this. Using the notions which we had previously, can you please tell me what does this look like? Just it was squared. I wrote it as the production of two expressions under brackets, right? This part, how can it be referred to?
Sigmoid function.
Thank you. And using our notions.
Sigma of ze.
Yes, and what is
p? The estimate of p. Why?
Great, thank you. And the second part, well, probably for now that's not obvious for you, but let's do it this way. Let's see what the second looks like. Let's add p1, py to this member and subtract py from it. It will not change the result for sure. Y plus py and minus py. So py is this, right? Minus py. Well, if we sum them up, I hope that's clear for anyone, that will get simply 1, because the denominator and denominator will coincide, right? Just they have the same denominator, and the 1 plus exponent of minus zy in both
Yeah, we
parts.
could just take the left fraction and divide it by exponent to the power of minus ze to get what we'll get.
Yes, we'll have 1 divided by 1 plus e in the power of z1, and the same as this. And by the way, 1 minus py hat is the same as taking the sigmoid of minus zy. That's what you're speaking about.
Yep.
Yeah. There it is. And so we can decompose all the expression, which will look like the production of py multiplied by 1 minus py. Let's find some space somewhere to write it. I'll do it this way. Our arrow will go like this, and totally we have this. Okay, so we have this, and this part is the only one we need to calculate. Let's find its value. It looks as follows. We have zy is this, the linear transformation of the input vector. And this equals just to someone, probably Mike. Okay, this equals just to xy. Since this member does not depend on v, and we have only the derivative of this part, this is just xy. Hope this clear. You are just so silent and no cameras. I cannot be 100% sure that everything is easy for anyone. Please don't be.
Oh, we're good. Good.
Great. So, and by the way, let's also find the derivative by vinyl. It will look like the same expression. If we take the derivative by vinyl, the result is someone.
Just one.
Just one. Great. Thank you, Maria. In this case, this will be just the derivative of this part by vinyl, which will be equal to 1. Okay, so we found all the parts of our chain rule. And let's just sum this up. Let's combine all the results we've got. That is the derivative of loss with respect to py multiplied by the gradient of py multiplied by, with respect to zy multiplied by the gradient of zy with respect to v. This, I will remind, is as the following video. This is py hat multiplied by 1 minus py, and as you can see, these two members will now kill each other. This is xy. So if we combine all of this, these members are the same, and since here we multiply, here we divide, they will disappear. The only things we have is py minus yi multiplied by xy. So this is the gradient of the loss with respect to our parameters if we have one input observation. We also need to do the same thing for vinyl. These two parts will be the same, right? They do not change. So we have this multiplied by the gradient of zy respect to vinyl. That's 1. So we simply have this. Now let's ensure that the shapes of the gradients are the same as the shapes of the parameters, that everything we've done now is right. Py is 1 is a scalar, yi is a scalar, xy is a vector of shape m by 1, right? So the total shape is m by 1, the same as the shape of our parameter. Great. Here, a scalar, the same as it is here. Great. So here are the derivatives of the gradients of the loss with respect to our parameters. Now let's extend this logic to the case of multiple observations and see what it will look like. So we'll have the same logic for each of the parameters, and it was here, I will recall, like this. Now we have several input vectors. P is now a vector without I, just P, of shape n by 1 or 1 by n, doesn't matter, to be honest. Y is now a vector of the same shape. And instead of having one input vector, we have an input matrix X of shape n observations and m features, right? So the total shape will be 1 by m, right? Here 1 by n, multiplying by n by m, totally we get 1 by m. An important thing is not to forget the rescaling, 1 by n, because when I had one observation, this part was equal to 1 and we throw it away. But for now, we need to restore it. And let's do the same thing for our intercept parameter. Again, the rescaling factor. And the only thing we had here was 1 by n, 1 by n, and totally we have 1 by n, right? Which is not good because first of all, this expression depends on the number of observations that we input to our model, which is not correct. And second, our intercept is a scalar, is just consists of one number, and here we have n numbers. Why have we got such results? If there is anyone who already knows, please feel free to describe, to explain. Okay.
So what was the question? I was watching.
The question is the shape of the gradient, which we get for vinyl, is now 1 by n, while the shape of the parameter itself is 1 by 1. What was done wrong?
What's the shape of the parameter?
1 by 1. That's the intercept.
What do you mean by shape? It's the shape of the estimate of P?
That's the shape of this parameter group referred to as intercept. So intercept is just one parameter, it's one number, but when we...
The intercept is not included in the gradient.
Why? We have the gradient of loss with respect to intercept, and for the case when we had only one observation, that was okay, but for the when we extend this to multiple observations, that's not okay. Okay, I'll explain this. So here we said the gradient is 1, and that's correct. But when we have a vector here, instead of just one observation, it's of shape n, right? And here is still only one parameter. And what is taking a gradient of a vector by one parameter? It means taking the derivative of each component of the vector by this parameter. So in case this is a vector, we'll have this the result of the taking the gradient will be also a vector of the same shape with each element of the vector equal to 1, since each of the elements of this vector will depend like this on on our intercept, right? So the result will just be a identity vector of shape n. This is an important moment, and if you have any questions, please ask it. Okay, hope that's clear.
So you said that the gradient of the intercept term is always 1.
I say that the gradient of the result of linear transformation with respect to the intercept is 1 for each observation. So here is the formula. Okay, let's.
Yeah, I see the formula, but the question is, so we calculate the gradients and we understand basically where to move our coefficients.
Yeah.
But with the intercept, we get, as you mentioned, we get 1. So how do we understand in which direction we move the intercept?
Yes, but that's not the full gradient of the loss with respect to the parameter. That's only the gradient of V. The full update rule is as follows. So that's the subtraction of the real class value from the predicted probability.
Yeah, so we don't need the gradient for the intercept. It's just the subtraction of the predicted value minus the actual value.
Why don't we need the gradient?
Okay, what's written on the last line? The py minus y.
Yes.
And it will be true, false. Like, where do we need the gradient for the intercept here in this formula?
This is itself the gradient of the loss with respect to the intercept.
Yes, but we we don't have to take any.
But here we also did not have to take just I see where you are going to. So neither V nor V nil do not take part in the gradient expressions. But how do we set the parameters of our network? For instance, using classical stochastic gradient descent or mini batch gradient descent, never mind. We get the gradients of the loss with respect to our parameters, and then we subtract these gradients from our parameter values multiplied by some small learning rate, right?
Mm-hmm.
So when we'll have to, on each iteration, which we will update our V as Vt equal to its result on previous iteration minus learning rate multiplied by this very gradient, which means multiplying by this, in case we have one observation in our batch. For V nil t, we have V nil t minus 1 minus n, or minus learning rate multiplied by this expression. Oh, pardon, there it is. So yes, neither V nor V nil do not take part in the update rules, but Py, while we calculate this, it itself depends on the values of the parameters in each iteration, right?
Yes.
Yeah, and the going back to the original question, this is the update rule when our batch consists of only one example, when Py is a scalar. And when this is a vector, when we have a mini batch of 32, 64 or more values. If we have the update rule like this, it will have the shape 1 by n, which is not correct. And it's not correct because generally this will not be 1. Generally, this will be the identity vector, which is a vector of size, the same size or as the a vector z of length n, which consists only of ones, and multiplying this by this very identity vector, if my memory serves me right, it is notioned like this. Please correct me if I'm wrong. And multiplying this vector by the vector of the same shape of transposed, which consists of ones, is simply means taking the sum of all the components of the vector, right? So we take each component with 1, sum them up, and there what we get. So under brackets, we have the shape 1 by n, and here we have the shape n by 1. So totally, we'll have the shape 1 by 1, which is exactly the size of our intercept parameter, and that's how we need to update. Okay?
Mm-hmm.
Great. I hope.
But anyway,
yeah.
Where is the gradient of the? Could you please return to the previous slide?
Yeah.
What the thing written in your top right corner, the gradient of the intercept. We don't need this. It's always the vector of ones.
Yes, but the fact, if we just throw this part away and say that the gradient of the loss with respect to vinyl is just taking these first two parts, it would lead us to the results when we have only this, and it's of shape 1 by n, while our
Okay.
parameter.
Okay. Else.
So we need to take the identity vector just to sum up the elements of the vector. Great. So let's move on. Here is the full update rule for the parameters of logistic regression on each iteration of gradient descent. And we have already written this. I do not need to do it once again. So these are the update rules for our parameters for V and for vinyl, right? But what if we want to have a stronger model, a more powerful model, which can do some more complex transformations with our data? We feel that we have the lack of parameters, probably the dependence between the target variable and the features is not linear. Probably you know that in practice, we very rarely find just exactly linear dependence. Much more often we have cases when dependence is significantly more complex. So let's try to do it the following way. For now, the forward pass of a model looked like this. Let's add some parameters and add another linear transformation before we do this one. So what I'm speaking about is adding one more linear transformation. So it will be like multiplied by, that's not the power, it's just the notion, vinyl, vinyl top or something like this to name this. This is the intercept of this. And after we do this linear transformation, we do another linear transformation. We do it like this, plus vinyl 1. Then we take the sigmoid of this. As for the shapes, here we had n by m, m by 1, 1 by 1. Okay, totally 1 by 1. Here we have n by m, m by k, k by 1. K is just an intermediate size to decompose. First, for instance, m is like 10. First, we decompose into 3-dimensional space, k is equal to 3, and then we from 3-dimensional space we decompose to 1-dimensional space. Here we'll have k by 1, 1 by 1. Here we had how many parameters? M for feature vector v and 1 for vinyl. So totally we had m plus 1 parameters. Here we have m by k parameters here, k, k, and 1, like this. Significantly more parameters, right? But is this model more powerful than the previous one? Can it model more complex dependencies? Okay, a big prompt. The result.
What we did, we just multiplied the. We did added additional weights. Well, no, we have the same. We have the same number of coefficients, isn't it?
Of coefficients? No.
Yeah, after all. Well, we have a coefficient where near each x, one coefficient.
Okay, I'm not sure whether I understood you right or not, but it seems to me you're describing the right thing, that the result of a combination of linear transformations is just a linear transformation. So we can add 10 more linear transformations here. Since they are all linear, we can combine this into one linear transformation. So this model will have a lot of more parameters. It will need a lot of more steps for the gradient descent to come to the optimum, but it has the same power. It's not better than the previous one. But How can we make it more powerful? This model is linear, so we have only linear transformations for our data, but nothing restricts us from doing our transformations non-linear. So we can add some non-linearity before we do the final linear transformation. What I'm speaking about is, instead of multiplying the result of this linear transformation by V1 and adding the intercept for V1, we can do the following thing. We can add the non-linearity for this result, and then do this linear transformation. So if we add some non-linearity in the just intermediate phase, the result will not be able to be expressed as a linear combination. So we just add non-linearity, and the result is not linear anymore. It cannot be approximated with linear transformations. There it is. So let's speak about main non-linearity functions. I think you know that they are referred to as activation functions in neural networks, just to see how they work. The most popular and the most simple one is ReLU. And this is an indicator function. It's discontinuous, but that's not the problem for neural networks. We'll speak about this. It equals to Z in case Z is greater than nil, and it's equal just to nil in case Z is less or equal to 0. So the plot of this function is as follows. It's just nil when the argument is lower than 0, and it goes like this. Using this cool geometry, we can write it like this. So, and it's equal to itself in case the argument is greater than 0. Another one activation function is sigmoid, which we have already spoken about. And its formula is as follows. And its plot looks like this. This is 1, this is 0.5. That's the sigmoid. Here it goes to 0, here it goes to 1. The third activation function, which is already very rarely used for now, but is still applied in recurrent neural networks and even in transformer models like BERT. That's hyperbolic tangent, which has the following formula. And its range of possible values is from -1 to 1. There it is. So these are the 3 most popular activation functions. And but let's speak about how each of them is applied in practice. To be honest, these 2 functions are very rarely used for now. Why? Because they require significantly more computations than the ReLU function. Here we need to calculate the exponent of each component of our vector in general case, then the exponent of minus value of each vector, then divide a lot of computations. Here we need to compute the exponent of minus vector and divide 1 by this, again, a lot of computations. In case of ReLU, no computations are done at all. So we just, well, okay, we compare each element with 0 and substitute it with 0 in case it's less than 0 and leave it as it is in case it's more than 0. Moreover, ReLU function is very powerful in that meaning that the absolutely any function, any difficult function can be approximated with many ReLU functions. So despite how complex your function is, if you take a lot of just combine a lot of ReLU functions, you can approximate this function very well. That's why ReLU is used significantly much more often on practice. And now some different modifications of it, like GELU or Liquor ReLU, are also often used. We'll speak about them later, not now. But now let's take just ReLU and add them to our new model and see what we will get. So here, let's get back. Before making the second linear transformation, we add the ReLU here. So the result is already non-linear, and our model can grab some non-linear dependencies inside our data. So in case that when the dependence is significantly more complex than just linear dependency, our new model will be able to get to grasp this very dependency. As for our logistic regression, it will not be able, since it's just linear transformation. There it is. And so these are how neural networks operate, how they work. What do they consist of? They consist of linear transformations and then activation functions, which add non-linearity. That's just the neural network. So we multiply, make linear transformation, apply non-linearity, do this several times, maybe 2, maybe 5, maybe 20 times. And then we update all the weights of our network using the chain rule. Let's quickly speak about the chain rule here. So we know how to calculate the gradients with respect to these parameters. We have already done it for logistic regression. Now, how to calculate the gradient for this, for instance, metrics. It will look, okay, not here. It's better to write it here. It will look as follows. With respect to the nil grade is the gradient of loss with respect to V1. This is known, that's it, multiplied by the gradient of loss with respect to, oh, I'm sorry, the gradient of V1 with respect to V new. And this can be again decomposed using the chain rule as the gradient of the ReLU result. So just the ReLU of Z nil multiplied by the gradient of Z nil by null. So this is how chain rule is applied. On every time we add linear transformation and non-linearity, when doing the back propagation, when doing the backward pass, when calculating the gradients of our parameters, what we do is we just apply this chain rule and find the gradient for each group of the parameters. Is this clear to anyone? Or probably this was difficult?
Yes, clear.
Great. I hope so. So this is how neural networks work. Of course, there are some difficult special layers, as you fancied them very much, like attention layer, like dropout layer, though it's very simple, which do not have the logic of linear transformation or adding non-linearity, but we'll speak about them later. They are just in, they can also be back propagated through, which means we can take the derivative of loss based on the parameters of these layers, and that's okay. As for ReLU function, which is a discontinuous one, when we will find the gradient of the loss with respect to its result, yes, it's not continuous, but there is no difficulty for computer to have it like, okay, if the input parameter was greater than nil, then its derivative is 1. For those parameters who were less than 0, the derivative is just 0. Why 0? Because we have this very expression for ReLU. And when our parameter is less than 0, its derivative is nil, which means that just not the derivative, I'm sorry, the result of ReLU is 0. So what's the derivative in this case? If we add a small value, epsilon, our function won't change since it will still be 0. That's why the derivative of ReLU function is 0, because despite a small increment of z, the result will still be 0. There it is. So discontinuous functions are not problems for automatic differentiation libraries like Torch, which can, they see that for some parameters, the derivative has one form, for some it has the other form. Okay, no problem. There it is. Okay, so that's the theory I wanted to embrace about the neural networks. I hope everyone understood this. And for now, we have one more topic to discuss. So I'm sorry to take some time of your break, but this will be important for now. We have to quickly speak about the extensions of the gradient descent for now. As I've already said, we'll not take all of the extensions which are not applied in practice, but let's speak how generally we can extend gradient descent methods. So the first group is, instead of, we can change the update rule. So instead of subtracting the gradient of the loss with respect to parameters on this very iteration, what can we do? We can use the result of the previous gradients which we got on previous steps as well, and taking them correctly will make our gradient descent significantly more stable, more robust, because if we always subtract only the gradient on the current step, when we have some bad examples like outliers or some just untypical examples in a batch, our gradient can be noisy. It can show us the wrong direction of minimizing the loss. And when we, it was like we were moving like this, okay. Then we have this bad batch, and then it goes back. And then we cannot return to the optimum point. That's the problem. So the first group of gradient descent extensions are intended on changing the update rule. And let's speak about the most popular method from here, momentum. You'll see why we discuss it. So it has the following formula. We have this this is the variable which will be subtracted from our parameters on each iteration. And let's see how it looks like. In classical SGD, we had simple learning rate multiplied by the gradient of the loss by our parameters. This is the loss, theta is the parameters, right? In momentum, instead of taking only this part, we also add the previous value of VT with some decaying factor gamma. It means that gamma is usually taken about 0.9, so that instead of using only the gradient on current iteration, we'll have this information on about the gradients on previous iterations, which are decaying with this very factor. So for instance, the gradient on iteration 3 steps ago on epoch t-3 will be taken with the weight 0.9 in the power of 3, which is about 0.72. Yeah, and the update rule is as follows. We take the params on the previous iteration and subtract this very value. There it is. So we use the information, we accumulate the information about the previous gradients by our parameters. There is also Nesterov momentum and so on here, but they are not important, and that's not obligatory to remember how they look like. Of course, that's good if you wanna read more about this, I can send you several very good articles where they all explain, but since we do not have much time, the time of class is already over, let's move on. And here, okay, let's say this group change the update rule, and the second group refers to changing the learning rate for each parameter separately. So we have a learning rate, such kind of element wise, and how can we understand which learning rate should be assigned to each parameters? To each parameter. The general logic is as follows. If the parameter had great values of gradients on the previous iterations, it means that it fluctuated very much. And for now, we need to diminish the learning rate. We need to decrease it so that we prevent it from fluctuating, from changing very much on each iteration. And vice versa. So if the parameter was not changing very much on previous iterations, probably it needs to be changed much now, and we need to increase the learning rate for it. Some methods which were spoken about on Coursera, if I'm not mistaken, delta, the grad, and so on, they are not important. Important is RMS prop. Though separately, this method is applied very rarely. We'll see how it is applied in combination with another. So what we do, we also have this kind of variable, expected value of gradient on current iteration, but this member, this also inherits the logic of accumulating the information on previous steps, as we did with momentum. In momentum, it's like taking with, okay, generally with the weight. No, RMS prop is always 0.9, if I am not mistaken. So we take the result of this variable on previous iteration with this weight, and with this weight, we add the square of gradient on current iteration. And the update rule for this very parameter, for one parameter on iteration t, is just the previous value subtracting the learning rate divided by the square root of this value plus small value epsilon. In case this part is close to 0, to prevent division by 0, we need to add some small value epsilon. And this is multiplied by the gradient, which we need to update. So, this part, it accumulates the square of gradients on previous iterations so that we can see if on with such weights above on previous 10, 15, 20 iterations, we could see that the gradient of this parameter was high. We need to slow down the learning for this very parameter. We need to decrease the learning rate. If vice versa, it was very little, it was not changing much, then probably we need to increase the learning rate so that if we see the if we see that it's not changing very much, probably we need to just make the training phase faster for it. That's the RMS prop. And now the last thing, and then I will let you go. That's the optimizer, which is used in 90 or probably more % of cases. I'm not sure about CV, but in NLP, in general deep learning, in speech recognition, it's used. It's just a ubiquitous method. It's called ADAM, Adaptive Moment Estimation, and it combines the idea of momentum and the idea of RMS prop. It has two accumulating factors, MT, which has the following formula. It's the beta 1 multiplied by the value in previous iteration plus 1 minus beta 1, accumulating the gradient on the current step. And it has the factor VT, which is beta 2 multiplied by VT minus 1 plus 1 minus beta 2 divided by the square of the gradient. So this member accumulating, it's the same as we had in momentum, which accumulates the information about the gradient itself to modify the update rule of the algorithm. And this VT, it accumulates the square roots of the gradients to be able to correct the learning rate element-wise. Some values for the constants. The authors of the method proposed 0.9 for beta 1 and 0.999 for beta 2, because this should not be very much dependent on the history, since the update rule needs to be we need to pay more attention to recurrent batch. While when we speak about the square roots or the squares of the gradients, we need to accumulate the information about a lot of more epochs and previous to see whether the value for this parameter was fluctuating significantly or not. If it was, then the learning rate for it will be decreased. And the final update rule is as follows. So we have parameters on previous iteration, and what we do, we subtract the values from this. But here we'll now speak about the head and what it is, multiplied by MT. Here is the full update rule, and as you can see, instead of taking only GT, only the gradient on the current iteration, we take this accumulated member, MT, which is taken from momentum algorithm. And here we divide it by this very factor taken from RMS prop. Why heads? Why just M head? Let's see. I will write now the formulas, and then we will understand how these formulas were obtained to make this process quicker. Let's see what happens on the first iterations. Okay, as for MT, that's not so dangerous. We have the previous, so M nil and V nil are equal to 0. So on the first iteration, instead of taking the gradient of GT, we take it only with the weight 0.9, and here is 0, which is this very 0, it refers to initialization. So it does not have any information. The idea of this variable is to accumulate the information about the previous gradients. But when we initialize, we have no previous information. We have nothing to accumulate. But anyway, this very factor is taken with a high weight, which prevents us from making the learning process good. But okay, let's leave it as this. Let's speak about VT. It has nil 999. So on the first iteration, V1 equals to nil, since we initialized it with 0, plus here is this multiplied by GT squared. While it was intended to accumulate information, we can see it just decreased the value on current iteration, and it simply increased the learning rate by 10 multiplied by square of 10, because the square root of this is just square root of V1 equal to 1 divided by 10 multiplied by square of 10 multiplied by GT. There it is. And that's not correct, because this factor, it doesn't accumulate anything. Okay, on iteration second, the accumulation factor will look like this. G1, okay, G1 squared plus, which is also a very, very small number, because this is even less than it was here, and here we had also a very small value. So again, instead of accumulating, we just diminish the results. Okay, we accumulate, but the sum of the accumulation is very small. It doesn't take part. It just artificially increases the learning rate, which is not good. So to prevent this, to make the estimates unbiased, we need to divide by these very factors. Let's see using VT here. So when we divide this by, this is the power, by the way, of t on the first iteration. When we divide by this value here, what we have is we divide this value by 1, which is just taking only G1 squared, because that's the only information we have accumulated so far. Let's calculate this on iteration 2, when we already have something accumulated. On iteration 2, it will look like this expression divided by this. No. There will have B2 squared, so it will be slightly bigger. It will be like something like this. And if you check this, when you divide it by this value, the sum of the coefficients of G1 squared and G2 squared will be equal to 1. So it means that the total weight of current and previous factors, which V2 is composed of, will be equal to 1, which means that great, we'll inherit this logic of accumulation, and the sum of all the previous and current values will be equal to 1. So initialization part, this 0 will not influence the total result. There it is. So this is the update rule for Adam optimizer, and that's the ubiquitous optimization method. Okay, any questions on here? Yes, so silent. I am always afraid that it was too difficult on some stage, and some of you just said, okay, I will not listen anymore. Okay, I'll hope this is not applicable in this case. So let's quickly, as we are already delaying, let's quickly see what we'll speak about on our next class. There will be almost no theory on the next class. It will be only practice, and we will write our neural network from scratch. So I will send you the notebook. If you want, you can watch it yourself before, then it will be even easier for you to understand what's happening on the next seminar. It consists of some inputs. While speaking about while describing the notebook, I'll show you some good prompts, some techniques from Jupyter Notebook, which will save a lot of hours of your life, like loading, some basic inputs, and so on. We collect the data, we examine it, we take only the numerical features for now, we scale our data. That's a crucial moment when working with neural networks. And we'll see that if we don't scale, we have bad results. We prepare some data sets, we build our model, we have some data, get the data loaders to batch sample instances from them, and then we write the train loop. But of course, to make this all, if we just have this notebook and I'll explain what happens on each line, probably you will understand what happens, but to the best of my knowledge, it will hardly teach you anything. You will hardly learn anything from this. So on our next seminar, we'll have some basic constructions. I will not remove them, but the majority of the notebook I will remove, and we will restore it together and it will be, that will be important for all of you to have your notebooks with yourself. I'm not sure for now whether it will be distant or offline class next time, since we need to, of course, I will send the notebook, and I will send our interactive desk results as well. And here we can see that a very basic primitive neural network outperforms significantly linear models like linear regression, rich CV, loss of CV, though I did not just specially take this data, which does not have such complex dependence. No, the data is very similar. It's a very popular data set, and even a basic neural networks can outperform all the linear models. There it is. Okay, so if you have any questions left, please feel free to ask them. If no questions, then thanks everyone, and I hope to see you next time. Yes, I think that will be on the 25th of September, but I still don't know about the date of our 6th class. And probably it will be next week on Wednesday, but I'm not sure for now. I will write in our Telegram chat all the updates for this. Yes, and another one reminder, those who do not have free access to Coursera, please write me your names so that I can send this information to the study office. Okay, so
Like when the test will be held, like in 2 weeks on the 25th?
Yes, I can tell you for sure it will not be next week. I guess it will be on a 3rd, 5th, and 6th classes, so that we have enough information passed.
Well, спасибо. Bye-bye.
Goodbye.